Question 13a. The solid metal sphere carries a charge of negative 2q. The net charge on the spherical conducting shell is plus 3q. What is the charge on the inner and outer shell of hollow spherical conducting shell? So here in this question, they have given you a solid metal sphere which has a charge of negative 2q, and I can write this as qs equals negative 2q. And this solid metal sphere lies in the hollow region of a spherical conducting shell, and the total charge of the shell, which we will write as q shell, is equal to positive 3q. We need to find what is the charge on the inner and outer surface of the shell. Now, the inner surface of the spherical shell is this region over here. And since there is a charge present at the center, which is the charge of the solid metal sphere, this charge will induce an opposite charge on the inner surface. So the inner surface of the shell will have a charge which is equal in magnitude to the solid metal sphere, but opposite in sign. So we can write charge on the inner surface Qi to be equal to negative of Qs, which is negative of minus 2q. That gives me plus 2q. So the inner surface has a charge of plus 2q, which is induced on it by the solid metal sphere. Now we can write the total charge on the shell, Q shell, to be equal to sum of charge on the inner surface plus the outer surface. And I can find the charge on the outer surface by subtracting these two. So we write Q on the outer surface equals Q shell minus Qi. Total charge on the shell is 3q minus charge on the inner surface is 2q. And when you solve this, you get charge on the outer surface to be equal to q. So we get q outer to be equal to q. Thus, we get charge on the inner surface of the shell to be equal to positive 2q. Charge on the outer surface equals q. And when you add them together, that is equal to the total charge of the shell, which is 3q. Now let's discuss part B. In the first part of part B, they are asking you what is the electric field strength inside the solid metal sphere. And in part C of the same question, they want you to explain your answer using Gauss's law. Now we know that the charge on the solid metal sphere is negative 2q. And they want me to find what is the electric field at a point inside the metal sphere. So let us take a point P, which is at a distance r from the center of the sphere. I will call this as point P, and distance of point P from the center is r. And since we need to apply Gauss's law, we are going to construct a spherical Gaussian surface passing through point P. We know from Gauss's law, the flux through any closed surface is numerically equal to the charge enclosed by the surface over epsilon naught. And from the definition of flux, we can write phi as integral E dot dA, which is equal to charge enclosed over epsilon naught. Since we are finding flux through the Gaussian surface, we are going to integrate E over the surface area of our Gaussian surface. So we write this as E times 4 pi r squared, where 4 pi r squared is the surface area of Gaussian surface, which is equal to charge enclosed over epsilon naught. Now, for a conducting sphere, in order to minimize the electrostatic repulsion between charges inside the sphere, any excess charge which is present is always accumulated on the surface of the sphere. So the excess charge of negative 2q here is accumulated only at the surface of the sphere. The net charge inside the sphere is always equal to 0. So the net charge inside my Gaussian surface is 0, as all of the excess charge are on the surface. So charge enclosed in this situation is equal to 0. So when you take 0 over epsilon naught, that will give you 0. So we get E times 4 pi r squared to be equal to 0. That gives me electric field to be equal to 0 Newton per Coulomb. Now this is true for any conductor because of electrostatic shielding. The net electric field inside a conductor will always be equal to 0. Now let's discuss part 2 of question 13b. What is the electric field strength within the spherical conducting shell? And in part D of the same question, we have to explain our answer using Gauss's law. So here we already know that charge on the solid metal sphere is negative 2q. And this metal sphere induces an opposite charge on the inner surface of the spherical shell. So charge on the inner surface will be positive 2q. We need to find what is electric field within the spherical shell. So let's take a point within the spherical shell. I will call this point as P, and the distance of point P from the center will be taken as R. Since we are going to apply Gauss's law, we will construct a spherical Gaussian surface passing through point P. We know from Gauss's law, flux through a closed surface is numerically equal to charge enclosed by the surface over epsilon naught. And from the definition of flux, we can write this as integral E dot dA equals charge enclosed over epsilon naught. Since we are finding flux through the Gaussian surface, when we take the integral, we are taking integral over the surface area of Gaussian surface. So we write this as E times 4 pi r squared equals charge enclosed over epsilon naught, where 4 pi r squared is the surface area of the Gaussian surface. Now charge enclosed by the Gaussian surface over here is the charge of the solid metal sphere and the charge on the inner surface of the shell. So we will add them to write the charge enclosed. We will write it as charge on the sphere plus charge on the inner surface of the shell over epsilon naught. That gives me charge on the sphere to be negative 2q, charge on the inner surface to be plus 2q over epsilon naught, which gives me E times 4 pi r squared equals 0. And when you solve this, you get E to be equal to 0 Newton per Coulomb. So the electric field within the spherical shell is equal to 0. And this expression will hold true even if there was no charge present at the center. So even in the absence of the solid metal sphere, if we were to find electric field within the spherical shell, it will still come out to be 0 because electric field inside any conductor is always 0. So as long as the object is a conductor, whether it is a sphere or a shell, electric field inside them will be equal to 0. Part E of the question. A solid metal sphere carries a charge of negative 2q. Derive an expression for the magnitude of the electric field E at a distance r from the center. So this is the distance r from the center that they have given you in the question. And we need to find the magnitude of electric field at this particular point. We are going to use Gauss's law to solve this problem. The charge on the solid metal sphere is negative 2q. To apply Gauss's law, we will first construct a spherical Gaussian surface that is passing through point P. And then we know from Gauss's law, flux through any closed surface is numerically equal to charge enclosed by the surface over epsilon naught. From the definition of flux, we can write phi as integral E dot dA, which is equal to charge enclosed over epsilon naught. Since we are finding flux through a Gaussian surface, this integral we will also take for the Gaussian surface. So we write this as E times 4 pi r squared, where 4 pi r squared is the surface area of the Gaussian surface, that is equal to charge enclosed over epsilon naught. Now the charge enclosed by the Gaussian surface is the charge on the solid metal sphere, which is negative 2q. So we write q enclosed to be equal to negative 2q over epsilon naught. E times 4 pi r squared equals negative 2q over epsilon naught. Divide by 4 pi r squared, we get E equals negative 2q over 4 pi epsilon naught r squared. So this is the expression for electric field at the given distance r from the center. And if we write 1 over 4 pi epsilon naught as k, we get the value of electric field as negative 2kq over r squared.